This lecture introduces linear regression, the idea of being able to fit a mathematical model where we use known values to predict random values. We're going to start with the very easiest case, something called simple regression, where we have one predictor variable and one response variable. And we're going to fit the simplest of curves, a straight line. So first we want to talk about fitting the line. Now the way we fit the line is with a process called ordinary least squares. Ordinary least squares looks at the bivariate model with a fixed predictor x and a random response variable y, with all the unexplained variation in the direction of the y or response variable. So you can see here, here's our variation up and down above the line. The values of x are presumed to be known perfectly. We define what's called a fitness function, a quadratic function, the sum of squared errors, and we take the deviations of the observed points and their corresponding points on the line, so vertically or above or below the point on the line. We take those deviations, square them, and add them all up to form the sum of squared errors. We'll expand that point on the line with its definition of the line. So there's our intercept, there's the slope times the x value. And then we take those differences, square them, and add them up, as I said. Now, the way we find the line is we're going to minimize this error with respect to both the intercept and the slope. We'll take the derivative of SSE with respect to each one, set them both equal to 0. We've got two equations and two unknowns, and we can solve those. When we solve those, we'll get the estimated model coefficients. The first solution we actually get is the one for the intercept. And so we see that the intercept is just the average y minus the slope times the average x. Now this is interesting because this solution tells us that the fit line passes through the point x bar and y bar, and that point's called the centroid. We'll talk about the centroid a little bit more later. The other solution is the slope. The slope, well, gosh, it's the sum of squares for the cross products, so the sum of x times y's, minus the sample size times the product of the means, divided by the sum of squares for the x's. If we take these definitions and plug them back into the SSE equation, we'll actually get a way to calculate what the sum of squared errors is. So you can see that we've got data here, and then we've got the intercept and the slope, which of course are also functions of data. And so completely from the data, we can get the sum of squared errors. Then we can get the variation around the line, we'll call it s squared for now, which is just the sum of squared errors divided by degrees of freedom, which in this case happens to be n minus 2. Here's an example. So someone did a study on rainfall and particulates in a particular region, and they saw that as the rainfall amount went up, the quantity of air pollution removed went down. Okay, it's kind of surprising. So here's our data. We've imposed what's called a low-S fit here just to kind of see the pattern, and we see it's a downward trend without any obvious simple curve. So we're going to try to fit a linear relationship, just a simple straight line. We'll start with summary statistics. So all of these things in the equations, we're going to calculate the mean of x, the sum of x squares, the mean of y, the sum of the y squares, and the sum of the cross products, and then we'll just plug them all in. We'll just plug them all in. And so we'll plug in for the slope first. That's the usual way to do it. And we'll get a negative slope, minus 6.324. Okay, at least the sign is correct. Slope's going down. And then we'll take that slope and plug that in, and we'll figure out what the intercept is when x is equal to 0, 153.175. Now, we can use this for a conditional estimate. Yeah, if you have an equation, you got to plug stuff in, right? And so we get what we call a prediction or fitted value, and we'll calculate when x is 4.8. So we'll put that in there, and we'll see, well, there's my intercept, slope times the value, and I get an estimate of 122.82. Now this is just a point estimate, okay? And you know from previous work in statistics that we want intervals and other sorts of things. So let's go figure out how to do those. What we need to do is do some kind of an inference, because thus far we really don't have anything that's statistical. So we're going to use a Gaussian assumption. The fit line is non-parametric. It's distribution free. All right, and so we need to have a distribution. Common practice says assume the y deviations are normally and independently distributed. Here's a summary of all this. Y is normal and independently distributed. The mean follows the line, the straight line, divided by slope, intercept, and the x values. And the variation is constant with variance sigma squared anywhere on the line. This allows us to do inference. We can do interval estimates. We can even do ANOVA. So let me see how this works. If you need to visualize this, here's the straight line, and then the variation follows a normal curve at any point on the line. So that fitted line is a point estimate conditioned on x. You tell me the x, I'll give you the point estimate. Well, that needs an interval estimate, and so here's the interval estimate using the Gaussian assumption. You can see that it looks pretty familiar. It's a t interval around the fitted point, and if it was any other kind of estimate, we just have s squared over n under the radical, but now we've got this extra little point. What's this extra little point all about? Well, the extra little point is about slope. So if we imagine this regression line, the slope can vary. The slope can vary. And as you see when the slope varies, the ends of the line swing a lot more than the middle. So how do we represent that mathematically? Oh gosh, here's the center, x bar, from the centroid, and here's our estimated point. This gets bigger the farther away the point is from the centroid. And so that gives us that swing out at the ends. Okay? And so that's the slope error. All right? And that's the way we get the estimate. So for our model, a 95% confidence interval says here's the point estimate, plus or minus the t multiplier times, those are sum of squared errors, 1 over the sample size. There's our slope error. And so when we calculate this, we get 122.8 plus or minus 1.76. Now we can calculate this at any point on the line, and that will give us our confidence interval. Notice this interval is narrowest at the center and it's wider out at the ends. Now, we can also do hypothesis testing. So there's a hypothesis test implicit in fitting the regression line. The null hypothesis is the line makes no sense, and the best way to estimate the average value of y at any point is just the average for y. The research hypothesis is, oh no, a line is better, and so our best estimate is the line. Our best estimate is the line. We can test this hypothesis with ANOVA, and so here's the ANOVA table we'll use. Okay, we'll start with the total sum of squares, which of course is just variation around the mean of y. Then we'll do the sum of squares for error. We talked about how to calculate that. That's the variation around the line. If we take the difference of those, we get something called the sum of squares for regression. So how much error is explained by the line? Degrees of freedom, n minus 1 overall, p minus 1 for regression. What's p? P is the number of parameters. Count the betas, in other words. And then you just take the difference here, n minus p degrees of freedom for error. Then, as usual, take sum of squares, divide by degrees of freedom to get mean square. Take mean square for regression, divide by mean square error to get an F statistic, which we can then test. A large F statistic suggests the fitted line is a better description of the conditional mean than the sample mean would be by itself. So here's an example from our example. If we look at the ANOVA table, we see you have 1 degree of freedom in the numerator and 7 degrees of freedom in the denominator. So at the 5% level, the critical value for an F-test would be 5.59. Here's our calculations. Total sum of squares is 804. Our sum of squares for error is 33.96. And the difference would be the sum of squares for regression, 770.26. Do our divisions by degrees of freedom, and we see we have a mean square for regression of 770, a mean square error of 4.85, and then the ratio of those two gives us an F statistic of 158.77. So this is way bigger than the critical value, so we'll reject the null hypothesis and conclude the model is good. Now, a lot of people don't want to look at all these numbers, and so they want a bottom line statistic, and we have one. It's called the coefficient of determination. No one actually says those words. They call it R squared. What is R squared? It's the sum of squares regression divided by the total sum of squares. So we get some number between 0 and 1. And this number is the fraction of the variation in response explained by the variation in the predictor. In this model, it's 770 over 804, so we get 0.958, okay, very close to 1. The coefficient of determination is one of those statistics that we like in Texas. Bigger is better, okay? So we usually try to get as large an R square as we can, but don't go overboard. Don't go overboard. It's useful to go from like 0.8 to 0.9. It's not useful to go from 0.95 to 0.96. Now, prediction. The model can be used for explanation. Slope is really nice for that sort of thing. But we'd also like to use it for prediction. Oh, people love to predict things, especially the future. Okay? Prediction is different from confidence. Similar to the confidence interval, we have a prediction interval. And it's almost the same equation. It's almost the same equation, except for the addition of this 1 right here. The 1 talks about variation not of the line, but of the data around the line. If we look at our model, we can calculate the prediction interval at our point 4.8, and now we see that the prediction interval is plus or minus 0.554, quite a bit bigger than plus or minus 1.76. Again, we can calculate prediction intervals anywhere along the line. And now what I've done is graphed both the confidence interval, the inner band, as well as the prediction interval, the outer band. The prediction interval is always larger than the confidence interval. This is a pretty encouraging graph because now we see that all of our data points actually fall within the prediction interval. Now, there are some things to be careful of when you're doing linear regression. So let's talk about a few of those. Inverse regression. Inverse regression. Once you fit a regression line, you cannot apply algebra and solve for x in terms of y. It doesn't work. The reason being is that the variation changes direction. The variation changes direction. If we try to fit those two lines, we'll see that they're not the same line. They cross at the centroid, but the two lines are different. Interpolation and extrapolation. Interpolation predicts a value within the range of the observations. In the range of the observations, you know your line is pretty good, and you can accurately estimate the error. So interpolation is no big problem. Extrapolation, on the other hand, predicts a value outside the range of observations. So you're talking about behavior in regions that you have not looked at. Extrapolation has two drawbacks. First off, the prediction interval gets very large. Remember that swing at the ends. The intervals get bigger and bigger as you go further out. But the other thing is that the shape of the curve is unknown. If you extrapolate past the end of the data, you have no idea if the line is going to continue in the same direction or if it's going to take an unexpected turn. So you have to be quite careful with that. Need an example? Here's an example. A young lady had no husband, then she's got one husband, and this fellow's going to extrapolate. By late next month, you'll have over 4 dozen husbands. Extrapolation is not always your friend.